Okay. Some kind of joke. Okay, so some of this is just review, right? So you know what homework 1 and homework 2 scores look like. Homework 3 are in the middle of grading. Hope to get that back to you guys for Thursday's lecture. There was 1, maybe 2 emails I forget about the due date for Lab 1. I totally spaced on giving you guys the data, so you necessarily couldn't have started it sort of right away. My only concern about moving due dates around is 2 things, like sort of your mental sanity. Do you really want this due later, really? And then whether or not that conflicts with other upcoming things, exams or things you have in other classes. So I think sort of letter of the law, right? This is going to be due on Thursday, I think. Does that sound right? Mm-hmm. So we can stick with Thursday. I can push it to Friday. I don't really mind pushing it back. Sometimes Monday due dates are terrible, right? Because then that's part of your weekend that you're spending working on this. So is there any sort of sense that you guys want more time or don't? Or yeah. So is Friday not enough, or would you rather just have the flexibility to turn it on? I'm okay with that. I just know what it's like to have or not have a weekend, right? I lose a lot of my weekends. Monday. But no one finishes early, right? Like that's the other. I'll leave it to you guys to figure out. Monday's fine. So why don't we have it due on Monday, right? You are going to get a homework assignment. You're supposed to get it today. I'll push that off till Thursday, right? And then typically only have a week for that. So things are going to be a little busy, right? You'll have the new homework assignment. You'll have the labs due, and then next week we have the last lab. So it kind of maybe eases off a little bit when you just have the last lab. So I'll make a mental note. Stick with that plan. Does that sound okay? Okay. Hopefully that avoids fine. I'm pretty reasonable, right? So if you tell me you have some other major whatever happened, then just tell me. So yeah. So then that was the next thing is I'll push out homework. I'll put off a little bit homework 4, which will go out on Thursday, and it'll basically cover like the last 4 lectures, starting a couple Thursdays actually, probably the previous 4. Anyway. Starting next week, we've got 2 weeks of lecture with invited speakers, and they're going to come talk about kind of slightly, either very research-oriented topics or sort of research / sort of cutting-edge techniques kinds of topics. That material is still important for the finals. I usually pull a question from each of those lectures, so I still expect that you're here paying attention and asking questions and that kind of stuff. But it's a little less maybe formal in some sense. The other thing coming up this week is next week rather, is lab number 2, right? And so that's scheduled for Wednesday. Sorry, it's a little confusing I've been clear in my slides, it's a little confusing how it's put on the website, but it'll be Wednesday again, just like the last lab. And these are the lab groups I would go with. We basically have switched the slot, so if you came early last time, you go late this time. If you came late last time, you go early. Normal. If you have a conflict, you simply can't be there, just let me know. I think I fixed the typos that we had before in terms of group assignments, so I think this works. It's mostly groups of 3, except for Kathy, you'll work with the Caroline groups, and she's a little bit late today, but the 2 of you will work together. But it's kind of a fun lab. Basically, you're going to get a protocol. You'll have a phantom that's in the scanner, and you'll have a protocol that's the baseline protocol, and it'll be a terrible protocol. And your job will be to sort of like improve that protocol so that you actually get a decent looking image. And there's a scoring system, so you're actually competing against the group that's on the other scanner for some extra points. So there's some motivations I can do well, and then of course you'll report about that as well. It's usually a pretty fun lab because there's some of the troubleshooting. And in fact, like this lecture, or at least the latter part of this lecture, will be important because a lot of that lab is going to be about artifacts and things that are terrible, what would it be, and how can I fix it. So this lecture in particular will be important. Questions about sort of assignments and how things are moving forward? I'll try to get you back, like I said, homework 4 really quickly, and then we'll get you back lab 1 as quickly as you can, so you have a really solid sense of where you stand, sort of before the final. I don't know if we'll have a last lab back. Good? Okay. The second thing was there was a couple questions back and forth. Someone emailed, I apologize, I wasn't always quick in getting back to people about this specific problem. This was problem 2 and homework 2, and the question about defining sort of frequencies and the dependence of frequencies as a function of space. And this question as to whether you had to solve this in a laboratory frame or the rotating frame. And there was some confusion about that, in part because the problem wasn't really specific. So somebody asked over email, and I gave a reply, and I said, oh, just go ahead and do it in the rotating frame. Effectively, it doesn't really matter, right? You're talking about a frequency range over space, and you're either adding the B0 frequency or you're not adding the B0 frequency. But the principle that underlies this mapping between space and frequency is really the same whether you look at it in the lab frame or the rotating frame. And so we're going to try to figure out a way, which will create a little bit of work for ourselves, but I'm fine with answering that question in either way. And so if you feel that you answered this problem adequately and appropriately in the laboratory frame and lost points, or somehow answered in the rotating frame and unfairly lost points, just touch base with me and we'll try to figure out how to make that adjustment. And we'll go from there. So hopefully that answers some of the concerns about that. I don't know how many of that. I don't know how many of you that affected. It's at least a couple people. So I just want to make that right. The real point being is I want you to understand the material, and in point of fact, it doesn't really matter if you did this in the lab frame or the rotating frame conceptually, as long as the other parts and pieces are placed. Okay? So if you have a problem or a concern about that, just contact me directly, and then we'll try to figure out how to address it. Yep. So the next thing, this is lecture 13, which is about image reconstruction. And so this is the lecture I asked you to watch online for last Thursday. So hopefully you did, in fact, do that. What I'm going to do is go through some of the key points. And the way you can think of this lecture is, if I'm talking about it now, it could show up on the final, right? So I'm trying to highlight kind of the high points. There's a lot of material in this class. MR is quite complicated. So I want to give you sort of a broad sense, but I obviously am not going to test you on on all of that breadth. So I'll try to hit on some of the highlights today about this particular lecture. So this was the learning objectives. I don't know what's going on, guys. Hopefully this isn't too much. And so this was sort of the end story of that image reconstruction lecture, and I'll get into some of the details as we go here, but this is sort of a high-level overview, right? So what the MR system is doing during the experiment is sampling the presence or absence, right? The magnitude of different spatial frequencies at different points in K-space. And it's not exactly obvious how we go from this acquired data to actually reconstructing the underlying image. And mathematically, it can be a little bit obtuse, the formalities of it. But what it really ends up looking like is something like this, which really looks like an inverse Fourier transform. And so remember, what we've measured is all these coefficients, right? We're moving through different points in K-space by adjusting our phase and frequency gradients such that we can we can step in increments of delta K, right? Either in the phase or frequency encode direction, we step in increments of delta K, and we do this through n steps, right? Where n is some matrix resolution, like 128. And so we're stepping from, say, minus 64 to something plus 63 in this case. We're stepping through those different coefficients, and then we're multiplying by the spatial frequency encoding, which is just this e to the minus I2 pi, something about K-space. And that tells us about whether this is a low spatial frequency pattern or a really high spatial frequency pattern. And in fact, the orientation of that pattern as well, right? Phase and frequency encoding allows us to adjust exactly what pattern we're trying to sample at a particular point in time. And then one concept that was further introduced was this window weighting here, right? And so we'll talk about this some more, but there's actually ways where if this is your acquired data, you're taking your coefficient, you're multiplying by the specific spatial frequency pattern you were trying to sample, and you could in fact introduce a weighting function. And that weighting function changes the properties of the imaging system slightly, changes the point spread function, for example, but it could have the impact of, in some ways, improving image quality, while at the same time probably having some slight downside as well. And so as regards that weighting function, what we figured out, and we'll just talk about in that lecture, and we'll see some examples today as well, is you can take your K-space data and you can dot multiply by some weighting function, sometimes we call it a filter, right? by dot multiplication, what we mean is this point down here is very low in intensity, right? This is a 2D surface, right? It's a 2D surface, it's high in the middle, and it falls off like a Gaussian, or similar to a Gaussian to the sides, right? And so in this bottom left-hand corner, it's very low in intensity, and that bottom left-hand corner is going to be multiplied by the bottom left-hand corner of this K-space data. It's point-to-point correspondence. In MATLAB, this is called dot multiplication. And so the action of that dot multiplication is going to produce Fourier coefficient data that is windowed or filtered in some sense by this weighting function. So you can see here now that your K-space data is kind of been smoothed over, right? The consequence of that smoothing over, we'll talk about sort of why this happens and whatnot. We get a little bit later talking about point spread functions and full width half maxes of point spread functions. The consequence of taking your K data, multiplying by a windowing function, and then doing the reconstruction is you can see the difference between the image on the bottom right and the image on the bottom left. The image on the bottom right is a lot sort of smoother, right? It's a little cleaner. And two things have really happened. You've pushed down the Gibbs ringing artifact, so we'll talk a little bit about Gibbs ringing. The Gibbs ringing artifact occurs when you do Fourier sampling at lower resolutions for high contrast objects. So low resolution and high contrast gives you this, it's a little hard to see here, we'll see better examples, but this kind of rippling effect where it's low intensity just adjacent to this high intensity region. There's a rippling effect. When you apply that windowing function, you can actually smooth out that rippling effect. The consequence is it will actually broaden the point spread function, and so your imaging resolution has actually gotten more poor. So you have slightly blurrier pictures here. And then it sort of just becomes this question of, well, what do you prefer? You want to do image interpretation on an image that's arguably sharper, or even technically sharper, but it has this ringing artifact, or do you want to do image interpretation on an image that doesn't have that ringing artifact, but in fact is slightly blurrier? And it's simply just a trade-off. Manufacturers, of course, anticipate that clinicians would rather look at this image on the right than this image on the left. As a scientist, you debate the merits, but each of the manufacturers has its own sort of flavor of filter functions that they apply. I don't know that there's a lot of secret sauce there, so to speak, but that's definitely part of their image reconstruction. And so this is, it was a bit of laborious math in the sort of online lecture, but this is the image reconstruction problem for MR. The image itself of the underlying object arises from the sum over all of the Fourier spatial frequency patterns multiplied by a possible weight, multiplied by the amplitude of that spatial frequency when you're acquiring the measurement itself. So this is the high-level summary of the image reconstruction problem for MR. Questions? Again, conceptually is what I'm really after. Okay, so another concept that came up in there was this idea of multi-channel reconstruction, right? We talk about having a coil, we have a head coil, we have a knee coil, we have a body coil. All of those coils, in fact, have multiple channels, multiple receivers that simultaneously obtain signals. And so a typical example is something like this. There's a nice, sort of ISO-intense, very uniform-looking image in the middle, but that image itself is actually the composite of images obtained from each of these individual coils. So these orange lines or orange bars represent the approximate physical location of an individual receiver coil. An individual receiver coil placed in this position, top left, is going to be more sensitive to signals that it's close to, right? It's going to pick up signals better there, and so it's quite bright, as you can see in this coil 1 figure, it's quite bright adjacent to where the coil would physically lie, and of course it doesn't pick up signals as well for more distant regions. It falls off something like R squared, and so you pick up signals close very well, and your sensitivity falls off. So depending on the physical location of the coil, obviously we'll be picking up a different physical part of the image information coming from the underlying object. But we can combine all of that information to give us sort of a more uniform image. And the combination strategy is relatively straightforward. And so this is highlighting in part that every coil has a unique sensitivity profile that might have identical electronic componentry, right? So it's physically built identically the same, simply because of where it's physically positioned relative relative to isocenter, relative to the object, they're going to have different sensitivity profiles. What we call the beam receiver field varies over a function of space. And you can see that in these underlying images. The other thing to remember is it's not just the receiver field that varies, right? So here in a simpler example on the top, we've got a receiver coil on the bottom, and it's highly sensitive to things on the bottom of the phantom, less sensitive to things further away. And on the right-hand side, the other circumstance, right? You've got a coil at the top of the phantom that's sensitive to that, and it's less sensitive to things that are far away. Sorry, I'll stop apologizing, sorry. And so this is the coil sensitivity profile for those two coils for that particular phantom. But it doesn't just, the coils don't just affect the magnitude of the signal you receive, they also can affect the phase of the signal that you receive. Why not, right? And so this is an example of phase maps, not magnitude maps, but phase maps that are obtained from those two different coils. So even though we think, based on the RF pulses we play, that our bulk magnetization should have a certain amplitude and be pointing in a certain direction, the magnitude can be colored by the receiver magnitude, the coil sensitivity pattern, and the phase can also be manipulated such that you get some underlying phase added or subtracted to the true signal. The ideal pattern, right, for either of these, well, I'll ask you guys, what would the ideal coil sensitivity pattern look like? What's that? Yeah, just uniform, right? You would just get uniform sensitivity across the field of view. Probably makes sense, right? Why would we want, as strong a signal as you can get from all regions? What about the phase map? What would the perfect phase map look like? The ideal phase map look like?
All the same phase.
Yeah, all the same phase. It might not really matter if it's adding like pi phase to everything or 37 degrees of phase to everything, but ideally you prefer not to have this variation in phase over the object. In the worst case scenario, this could actually cause some trivoxel dephasing, right? If the phase gradient was sharp enough, you have different phases received for signals that are otherwise coherent inside your pixel, and that can cause signal acceleration. These gradients tend to be relatively smooth, and that's not a huge problem. So we can just look at one more example here. So here we've got a cardiac coil. We're thinking about acquiring cardiac images. Each of the coils placed anteriorly has a receiver sensitivity or coil sensitivity profile. We can place two coils posteriorly. They also have different coil sensitivity profiles. So this is just a map of, in this case, sort of a theoretical coil sensitivity profile. And each of those coils will acquire a slightly different image, right? It's the same underlying object, but the magnitude of the signals received is colored by the specific location of the gradient of the coil itself. And then those can be combined to form, here in just a second, to form a much more uniform looking image, which is the sort of final reconstructed image. And the reconstruction process, I mean, there's a lot that could be said about the reconstruction process. We give it a reasonably light treatment in this course, so 229, if you take that next, we'll go into this. I think it goes into this in more detail. The basic process is really just something like this. We'll have the acquired case space for every coil, right? Every coil is a separate receiver. Every coil is written to disk, if you will. There's a separate ADC, and then all those signals are acquired basically independently. We can then take the inverse Fourier transform of the coil data and get individual images. So now we have an image for every coil. And the question is, how best to combine those coils together? And the answer is relatively simple. We just sum up the magnitude squared of those images, but we correct for by the noise variance. And the reason you want to correct for by the noise variance is there's the possibility that one of your coils will be corrupt, poorly performing, really distant from the object, something such that it has more noise than other coils. They won't necessarily all have the same noise, sort of baseline noise. And if you have a really noisy coil, then this variance will be really high, and you want to push down that contribution, the contribution of that coil's image to the overall image that you're reconstructing. And if the noise happens to be really, really low, then this term will contribute even more for the jth coil, and that'll add more information to the overall reconstructed image. So it's just a weighted square root sum of the squares. And that noise variance, I mean, it can depend on what we call coil loading, how close the coil is to the object, similar to the proximity to the patient. And we can measure that noise actually with the noise scan. So you'll hear it when you're running the scanner in lab. There's always a little extra buzzing and clicking. You'll know when your protocol is running because it's sort of just continuous. But usually before that, there's some clicking and buzzing, and there's some calibrating and some noise scans that can be run. So you can get an easy estimate of this noise scan. How do you think you would measure the noise? Like, what do you think the scanner is doing when it needs to know the noise for a coil? What kind of pulse sequence do you think would be useful for that? So you don't really want a lot of different transverse magnetization states, right? You don't really want much image information at all. So proton density would be a good guess, right? So you could do a proton density scan where you wouldn't even have to run, a fully encoded image scan. You could just, get a few lines of K-space. So that would be a reasonable way to do it. In point of fact, you don't even have to do that though, right? You could just simply turn on your receivers, turn on each of your individual receivers with no excitation, no gradients, and just listen for baseline noise. So that's the even sort of slightly simpler way to do the same thing. I really try to list this from today. And then once you have some estimate of the noise variance, then you can use that as basically as a weight in that reconstruction. So this is what we call multi-coil reconstruction. And this is typical of all MR systems. It's perhaps the simplest way to reconstruct the images, or combine rather multiple coils. There's far more complicated ways to do this now as well, but it's a starting point. Questions about this? And so the other part of that lecture, I think the multi-coil stuff we didn't get into too far in the online lecture, so I wanted to touch on it a little bit more. In the Liang and Lauderer book, he sort of poses it this way, the overall image reconstruction problem, right? He says that you're going to measure a bunch of signals, right? In our case, we're doing Fourier sampling, but in the more general case, you could just be measuring some signals, projections, photon counts, whatever. And your system will have some kind of spatial information encoding scheme. In our case, we do Fourier sampling, but there's all kinds of possible spatial information encoding schemes, right? CT does it differently than MR does it differently than PET does it differently than SPECT. But what we're really interested in is not really the measured signals themselves, but the fact that those measured signals tell us something about the underlying image function. And so this is just a kind of mathy, formal statement for what we call the data consistency constraint. So we think or expect that this has to be true in the case of fully sampled data for an underlying object. And the trick is really the inversion of this, right? How do you recover the image, the thing you actually want, from all of those measured signals? You have to understand how to invert all the data that you acquired. You know how you encoded it, so obviously that gives you a heads up, right? We know we were trying to do Fourier encoding, and so then the previous lecture sort of got into the details of this inversion process. And you've seen this before, right? So this is a really important equation. We've maybe seen it in slightly different forms, but this is really important equation for this class, right? This is the MR signal equation that tells us, in this case, the signal that we're measuring at a particular point in time depends on the state of the transverse magnetization, right? All of our pulses, and the spatial frequency encoding that we are applying at a particular point in time. And the spatial frequency encoding has this delta omega term in it, right? It's the range or the delta frequency that we're sampling at that particular point in time. And in point of fact, we map this out as a function over space, right? All points in space that we care about, we can just re-express it, and it looks a little bit more like the 2D Fourier transform, because now we're saying the only space we care about is x and y. This is sort of the two dimensions in the plane of the image that we're trying to obtain to generate the image itself. And then this process of understanding the Fourier encoding approach, we understood that this delta frequency that we're imposing on the system, right, we're forcing there to be a range of frequencies or a range of phases as a function of the frequency encoding and the phase encoding gradients that we apply. And so the range of frequencies that are generated depend, of course, on gamma, the gradient that's applied, and then where you are in space. And we can do this in two directions. We can do this in the x direction, we can do this in the y direction. And it's all these linear combinations of x gradients and y gradients that let us get to different points in k-space. So in this case here, it looks like a 2D Fourier transform, but we can make this substitution and make it more of an MR problem and say, well, what's the delta omega that we care about really is governed or driven by the applied gradient waveforms themselves. And then it's really kind of by substitution at that point, right? We say, well, all of these frequencies that we're generating, those are frequencies that vary over space. We're going to call those spatial frequencies. And in fact, we're going to make a substitution and just use this k-space variable as a way, as a proxy or as a stand-in for the product of gamma over 2 pi times the applied gradient and the duration during which that gradient was actually applied. And so this is sort of just, in some sense, it's just a convenient nomenclature, right? We make this substitution and start calling a bunch of those variables the k variable or the k-space variable. And so the final expression for this would look something like this. We've gone from S of t, a time-varying signal that we measure, to an S of k, telling us what's the amplitude of the Fourier coefficient at different points in space, and it really looks like a 2D Fourier transform of the state of the transverse magnetization. And the state of the transverse magnetization really is the image that we're trying to obtain. We've tried to manipulate the contrast in the transverse magnetization, and now we try to get this snapshot by moving around all different points in k-space and getting all of those signals. So that's the sort of the series of mathematical events that where we recognize the signal equation in the form of a 2D Fourier transform. The problem, of course, is really the inversion process. We know what we measured. How do we actually get back to forming an image? And so there's slightly different ways to write the same thing. We can write S of n, where n is just like an index, right? It's the first k point, the second k point, the third k point, fourth, whatever. Or it could be a 2D array, n by m, right, for the different points in 2D k-space. And so this is what we actually measure, right? We measure signals as integer multiples of some delta kx, right? What was delta kx related to in terms of sort of our imaging parameters? What's it most closely related to? Field of view, right? So we care a lot about delta kx because we have to have the right field of view for imaging our objects. So this is sort of just putting it into that discrete form, saying we'll sample these discrete points in k-space where n is an integer, delta kx is our step size related to our field of view. Of course, what we really want is the image of this thing, right? We're trying to pull out this image, so how do we actually go about doing that? Well, it's a little bit obscure, right? So the steps to get there, in some sense, are terribly important. I almost hate saying that out loud, but in some sense, not terribly important. And what we can get out of this, you can go back to the Lauterbur book to see that, in fact, if we add up the Fourier coefficients multiplied by their spatial frequency sampling pattern, right? So some magnitude, if you will, multiplied by some spatial frequency. If we add all of those up, in the absolute sense, from minus infinity to plus infinity, then that's equal to this thing that looks a little crazy, but it really is representing the image of our underlying object. Because these Fourier spatial frequency sampling patterns they're just mathematical functions, right? So they're just some sampling pattern that goes from plus infinity to minus infinity. In the pure mathematical sense, what this represents is what we call a periodic extension of the underlying object, or the underlying image I. And that just means mathematically you have your image that you perhaps really care about in the middle of your spatial domain, so the plus minus either side of 0, and then there'll be another copy of your image and another copy of your image, because these Fourier series obviously repeat the image itself, or in fact repeat. Not a big deal mathematically, we just truncate it to the field of view that we actually care about. It's more of a mathematical sort of precision case. So this is the same expression we saw just a second ago, and again, just sort of a conceptual reminder that the image reconstruction problem really looks like this. We've measured all of those k points, their amplitudes, and we're multiplying those by all of these different patterns that we think we sampled, right? We drove our gradients to visit different points in k-space, so we should have hundreds, thousands of these patterns that we sampled, and we measured their amplitudes during the frequency encoding part of the experiment. And so, again, this is actually sort of showing the same thing I was discussing just a second ago. that the actual mathematics of the image reconstruction problem suggests that there's a periodic extension of the object, or the image of the underlying object. Not a big deal. All we do is reconstruct over the spatial domain that we really care about, which is our field of view. If we were to extend the reconstruction problem past the actual field of view, we would just see our object appear again and again and again and again to the limits of what we decided to reconstruct. So bottom line, we just sort of truncate this thing so that we get back the image that we actually care about, which is just a single replicate in the middle of the spatial domain. A lot of what was shown there previously sort of had these infinite limits on it, right? So in the purest mathematical sense, we think of things as possibly being plus minus infinity, but that takes a lot of time if we're going to sample infinite k points or infinite periods of time or infinite matrix points. And so we obviously do discrete sampling. And so this is just saying that the domain that we actually acquire on is in steps of n delta k, and we step over where n is from minus n over 2 to plus n over 2, and big N is the total number of matrix points, right? So when you sit down at the scanner, you basically specify your field of view, and you specify big N. Big N is the matrix size. Do you want your image to be well represented by 128 points or 256 points? That's something you have the freedom to choose. So N is really just the number of sample points. And so then finally, and this is kind of the perhaps the biggest highlight for this part of this section of this lecture, is just saying that finally the image that we care about, right? This is what this whole class is built up to in some sense. The image of the object itself just comes out of the sum of the Fourier coefficients multiplied onto the spatial frequency patterns themselves. And if we add all of those up, we'll in fact recover the object that we care about. And this really just looks sort of like a 2D, looks like a 1D discrete inverse Fourier transform. So mathematically, there's a 1-to-1 before those two. So really, this is in some sense the fundamental image reconstruction equation for MR. The nitty-gritty details of how we went from the sort of consistency criteria that was shown 8 or 9 slides ago to getting to this point here is, I think it's important, especially if you want to be an MR scientist, to procedurally understand how these things work out. But this is obviously well accepted and sort of well known at this point. So this is the sort of the end point that you should be familiar with. You should sort of understand those terms and sort of appreciate why that's a satisfactory solution to image reconstruction. Questions about this last equation? The terms are, what it means, or things from. You saw, I think, an example already, right, in homework 3 about using these for sort of generating spatial frequency weighting patterns. Yes? Okay. No? Maybe that's coming up then. I showed you some examples in class, but that's okay. Well, it wasn't in the last one. Okay. So, it's okay. So I'll talk through, again, this is, trying to do something of a quick summary of the previous lecture, and then we'll probably do this for another 10 or 15 minutes, and then we'll take a break. So one thing we obviously care about in MR is spatial resolution. So what does spatial resolution mean? For an imaging system, it's the smallest separation delta x of 2 point sources necessary for them to remain resolvable in the resultant image. Right? So if you can't resolve the separation of 2 points in an image, they blur together in some sense, and that's below the lower limit of your spatial resolution. And so if you look on this screen, there's 2 point sources here, there's 2 point sources here, and there's 2 point sources here. So you, as if you take your own optics into account, you will or won't have the ability to resolve 2 point separation between those different things, right? You have some associated point spread function for human vision, your specific human vision, right? And in fact, in this case, it will depend on how close or far back you are sitting in the room. So I won't ask who can sort of see what, but there are, I promise you, 2 different points in those 3 locations. And so the problem of spatial resolution can be sort of summarized this way. We have some object, right? The object is the thing that's in the scanner. And we have an imaging system. And the image that we actually obtain of our underlying object will depend on the point spread function of the imaging system. So some imaging systems or each imaging system will have its own point spread function, and in fact, we can usually make some adjustments to the imaging system to improve, that is, narrow the point spread function, or in fact, broaden the point spread function, so that we can have lower or higher resolution images of the underlying object. The object itself is sort of infinitely resolvable, right, at least down to some atomistic level or something like this. But the imaging system itself will have a point spread function that limits the actual practical spatial resolution of the system. And so if you're not familiar with this concept of convolution, this is one way of describing it. We have 2 points that are well separated, say twice the width of some point spread function. We'll talk more about this in a second. If we convolve those 2 point sources with this point spread function, then we can see that we would be able to resolve and separate, that is, those 2 points as independent sources of signal. As those 2 points get to be close together and in fact get to be the width of the point spread function itself, then the convolution will show us that in fact those 2 things just begin to touch, and so they effectively blur together. So point sources that are separated by W with an imaging system whose point spread function has a window width at W really can't quite be resolved. And then it just gets worse, right? If those 2 points are even closer together and you convolve those with this point spread function, now they're blurring together even more so. And this is always happening, right? We're always blurring something because we don't have infinitely resolvable imaging systems. The question is, how bad is that blurring and how does it relate to actual acquisition parameters? And then it stands to reason, based on the previous equation, that the image of the underlying object, those are only going to be identical if, in fact, your point spread function is just a delta function. You just have a perfect delta function. In that case, the convolution is just shows that those two are equivalent. Now, when it comes to point spread functions, every imaging system will have its own point spread function. And in fact, we can change the point spread function of the MR imaging system because we can adjust the matrix resolution, we can adjust the field of view, and those things will give us different resolving capabilities. And so one way of characterizing the resolving ability of an imaging system is to describe the resolution limits of that imaging system through a window, what we call the width of its point spread function, WH. So H was the point spread function, W is some measure of its width. And broad point spread functions will blur objects or blur the underlying object. And really narrow point spread functions will not blur as much. Obviously, we would like to not blur as much, but we'll see sort of what the penalty associated with that is. There's different ways of characterizing the width of the point spread function. One is what's called the full width half max. And so if our point spread function, if the imaging system itself has a point spread function that looks something like a Gaussian, then we can talk about how wide is it at half of its maximum, what we call the full width half max. It's just a real simple way of saying what's a good measure of its width. There's other definitions as well where you can take the integral of that point spread function itself and divide by its maximum. And that's just another way of describing really what looks like a box function with the same height and area as your h of x. So not too important, but just helping you get some grasp of what the window width really means. Now, through a fair bit of math that was in that previous lectures in the book as well, we can describe the point spread function for the MR system that's using this Fourier sampling strategy. And what it ends up looking like, there's an approximation that shows up in here, but this is the approximate point spread function for the Fourier sampling strategy. So you see the sort of funny sine over sine business, which actually is this is actually equivalent to what's called the Dirichlet function. Dirichlet function looks a little bit like a sinc function, so you can sort of think of it as a sinc function. And we can just map out what this function looks like under different conditions, right? And so let's think about what these parameters mean, right? There's really 3 parameters in here, right? There's big N. What's big N? Number of matrix points, number of data points that you're sampling, right? The number of points that will ultimately form your image. What's delta K related to? Field of view, and then X is just some spatial dimension, right? So this is, we're just thinking this in the 1D sense. So in this case, I'm plotting the direct function as a function of X, but if I want to do that, I have to pick two other parameters, and so I choose an N of 16 and somewhat arbitrarily choose a delta K of 1. So this delta K will set my field of view that I'm trying to image over. And by choosing N equals 16, in the MR sense, is a very low resolution image. So this is a plot of the approximate point spread function if I choose to do my encoding with 16 points for this specific field of view. I didn't put units on this, so maybe this is 10 centimeters, maybe it's 10 meters. It doesn't really matter. The point spread function looks something like this. So what does this mean? Well, you're taking your object, and every point in your object is going to be convolved with this point spread function. And what does that mean? Well, that means that that point in your image is going to be well represented at its specific location, but it's going to broaden out, and in fact, it's going to sort of wiggle, it's going to have information that sort of blurs into adjacent spatial positions, right, distant spatial positions, such that the signal, right, the paired magnetization at the center of the center position here will actually kind of spill over into adjacent voxels. If this thing was, if this looked like just a Dirac delta function, it would say that the signal at that location stays exactly at that location. But because I'm convolving the signal at that location with this funny sink-like thing, it means my signal is sort of spilling out into adjacent pixels. And every pixel is similarly spilling out into its adjacent pixels. So let's look what happens if we choose different sampling strategies, right? So here, I've kept N equal to 16, but delta K changed to 2. What happened to my field of view? Bigger or smaller? Went smaller, right? So my field of view is 1 over delta K. So delta K went up, field of view went down. And so what you see is that your point spread function actually gets narrower, right? If my field of view got smaller, but I still sampled the same number of points, my resolution is improved, right? The dimensions of my individual pixels have gotten smaller. And so you see here that you have this narrowing of the point spread function. You still have a silly ringing problem, right? Meaning that information from one pixel sort of bounces out into other pixels, and all pixels do that. So there's this funny sort of blurring happening, but that's the consequence of Fourier sampling, at least as it's written here right now. So we can keep going, right? So in this example here, let's keep this as the baseline example, right? So this is my baseline example. How has my field of view changed? Hasn't changed, right? Delta K is the same, field of view hasn't changed. So what did change was N. And it's my matrix resolution, right? So I kept my field of view fixed, but I said, I'm going to sample it with far more points by a factor of 4. What happens to my point spread function? Wider or narrower? Narrower, right? Makes sense. I'm encoding the same field of view with far more points. I must have smaller pixel sizes, and consequently, it must be the case that the full width half max of my point spread function has gotten narrower. That individual pixel is more well represented at that specific spatial location. It still bounces out into other adjacent pixels, but it's really well resolved at that narrow pixel dimension. And then maybe one more example here, right? And so this is sort of, again, in reference to this example here, what happened to my field of view? Got smaller, right? So my field of view got smaller, and my number of encoding points went up substantially, right? And so now I have a really narrow point spread function, right? If I look at, if I try to characterize, the full width half max of this top left case versus this bottom right case, I should see a difference of, 8 or something like that. So my matrix resolution went up by a factor of 4, and my field of view changed by a factor of 2. So the approximate width of this top left function is about 8 times that of this bottom right function. So this is all just mathematically pointing out that when we do Fourier reconstruction, this is the approximate point spread function that we'll get from that system, and the resolution really will depend on the number of encoding points and, of course, the field of view. That part shouldn't be too surprising at this point. When we do the Fourier reconstruction problem, we can describe the window width we were talking about like the full width half max, or there was another expression which was an integral expression for the width of that window function. And if you solve this integral for the point spread function that was on the previous slide, it actually reduces to something pretty simple, which is just to say that the width of our point spread function is just 1 over n delta k. Okay, let's think about that. So 1 over delta k is what? Field of view. And so this is just field of view divided by n, the number of points. And so the end-all be-all of this, this in fact defines what we call the Fourier pixel size. We're using Fourier sampling. This is what our pixel size is. And it kind of gives, in some ways, it's kind of an unexciting sort of dull result. It basically says that the Fourier sampling works. That's basically what this expression says. Fourier sampling works because the width of my point spread function is what I would hope for. It's my field of view divided by the number of points. Right? So it's a relatively obtuse way to maybe sort of get to that conclusion, but that's what you would want, right? It would be unfortunate if you did all of this encoding and in fact ended up with a blurrier image than you would expect to be represented by the field of view divided by the number of encoding points. So it's a roundabout way of saying Fourier encoding works. Would be surprising were it not the case. So this is actually sort of restating what I said just a second ago. And I mean, this is perhaps obvious too, but you can't reduce the width of that point spread function and reduce n simultaneously, right? You'd like to have higher resolution. You'd like to acquire fewer data points, but those two things obviously don't go together. So your choices are sort of as follows. You can increase the spatial resolution, that is a narrower point spread function, but the only way you can do that is to either increase the number of encoding points or decrease your field of view. Typically, we have a limit on our field of view, right? The field of view has to encompass at least the object that we care about because we don't want the aliasing. So our fields of view are relatively fixed for a given object. And so really the only way to adjust the width of your sampling function is to pick a different encoding number of encoding points. And so we can do that. We'll see this on the scale. You can pick that however you want. And then this last thing is just a restatement, sort of the opposite case restatement. And so, just sort of backing up a little bit, right? So practically, when we do finite sampling, we have choices, right? One choice is that we can sample just a smaller number of points, what I'll call in the middle of k-space, and the Fourier transform would just be this sort of blurry image that's here, right? I haven't gone out to the edges of k-space. I haven't encoded higher spatial frequencies. If I take the time to increase my n, I can narrow the width of my point spread function. I have to, if I'm going to increase n, I have to take more time to sample more points, and I can get farther and farther out in k-space, and I could fundamentally resolve a much higher resolution image of my underlying object. So let's do a little thought experiment. For those two examples that are shown there, what's the same between the two acquisitions and what's different? So if we look at the sort of parameters governing the width of the point spread function, what's the same for these two acquisitions and what's different? So we can pick one. What about n? Is n different?
Yes.
Yes, right? So is it higher or lower here? Lower, right? Obviously higher here. What about delta k? Is delta k different between these two? Why?
Because your matrix size in the end, it's getting the same amount of same area of information, right?
It's getting the same area of information, yeah. Agree with
It's
that.
not the same resolution because you're not getting as big of a matrix.
Yeah, so here you're not getting as big of a matrix. Here you're getting a bigger matrix. So I think we're agreeing partly. But if we want to say that delta k is the same between these two, what else? What's another way of saying that? If delta k is the same, then the field of view is the same, which I think you were getting at, saying the data is the same, the information is the same. And so obviously the fields of view are matched here, and so that tells me that delta k is the same. And then it's a question of k max, right? How far out in k-space did you go? That's what's different. And going out farther in k-space takes more time. It's either a longer readout or more phase concepts. So we can link this back. This actually goes, I think, 2 lectures ago when I was last Tuesday, to how do these parameters that we care about actually relate to the gradients that we're steering and using to move around case space. And so we saw this before, but the delta kx, which we know is related to one little field of view x. X we usually think of as the readout direction. It's a little bit arbitrary, but that's kind of convention. And so what are the field of view constraints during readout? Well, we pick our field of view. That dictates our delta kx. What governs delta kx is the magnitude of the readout gradient and then the delta t, the sampling time that you use at each of those sort of points in the case space. And then we can look at the sort of other direction, which is the phase encode direction. And of course, it's still the case that delta ky dictates or governs our field of view. What really physically changes our delta ky is the phase encode gradient step size and the duration of the phase encoding gradient. How long did you apply that phase encoding gradient? And so practically, we don't really pick our delta kx or delta ky, we pick our fields of view. Behind the scenes, the scanner makes calculations about what should our delta t be, how long should I sample my signal at each of these points in case space, and that depends on things like the applied gradient strength, and then I might need to calculate as well what's my delta gy, what's my step size in the phase encode direction, and that's going to depend on how much time you allow for phase encoding, and then something else that you already picked, which was the field of view. So just some algebraic expressions about how we actually calculate or choose some of the whole sequence parameters themselves. Again, we don't really pick these. These are how they're calculated for the things we care about, field of view, matrix size, etc. Okay, so that's the sort of review of last Thursday's lecture. Questions about where we are at this point in time? Tried to keep the conversation going. So we're right at the hour. Why don't we take a short break, and then when we come back, we'll go through imperfections and artifacts, and this is fine. If we don't get through all of this, it's fine because it fits in well with the next lecture as well. So at any rate, we'll come back to this in a few minutes. Okay? Yes, no, that's yeah, so yes, x is especially x is from say this is an and so this expression is just saying what's the range of x. So we saw this a couple times. So if you're moving is equal to x that we care about has to be x that we care about is going to be, we could write this as less than the field of view, right? So we don't, in this form of imagery construction, we're not thinking about spatial positions outside of the field of view. If you were to plug in x's that were outside the field of view, you would end up with this situation here, and you can see your image repeating itself. Because these coordinate elements. Yeah, so I think this is the problem that a couple of the students were asking about, like that the TA sort of brings them up saying and I can look at it more carefully, but I think this is maybe you should. So this you've done this in the rotating section. So it should yeah, so just yeah. So just send me a to this. Yeah, I talked with her a little bit about it, so I think I'm not sure where the confusion came out, so I don't want to try to like figure out what happened historically, but rather just to think about potentially how we're supposed to handle this problem, right? So we have the B effective. So oops. It's like omega root plus B. Right? And so in this problem here, the thing we often have to think about is like B0, A half. I have to write B1, right? It's on the I, J, it's very important J directions, and then we have G, X, so X, and that's a direction. In this problem, we don't have, right? And if you should include B0, then it just cancel out this term. I mean, you should still just be term. That's fine.
Okay, so we can still have
Absolutely. Yeah. Let me just get a quick
Oh, she's watching? She's like a super fan. She can check online.
Well, I don't think ultimate. Yeah, I mean like all the dental gels and stuff too. I don't think so. They purchase a printer and they email us saying they need more stuff. Yeah, Ream sent it as an edge. It was the sole source justification, which I already had written, and we signed it. But I asked them at the beginning, is there anything I need besides these forms? Let me know. And I said specifically, as an example,
Right.
this form. They're like, oh, no, it's fine.
Okay, it's easier to say that.
Yeah, and that's like, you need this form.
Cool. All right, let's go ahead and get started. So there was a brief discussion on the side here, just about homework 2, problem 2, and whether or not you have to do it in the rotating or laboratory frame, and some confusion. I don't want to try to sort out sort of what the confusion was per se, rather just state more clearly forward thinking what is acceptable, appropriate, what's the physics, what's the math. And so normally we talk about be effective, right? Be effective. Oh, we don't normally. We talk about be effective when we're considering problems in the rotating frame, right? And the definition of be effective was this fictitious field, this thing that we went through a long derivation for it, but the point is that there is a so-called fictitious field that offsets effectively the B0 field. And that other component of be effective is not just this fictitious field, but also this, what we call B rote, which is transformation of the applied fields into the rotating coordinate system. So B0 can be transformed into that coordinate system. That's easy because K hat and K hat prime are shared in between those two coordinate systems. RF pulses, which I crossed out because they're not actually relevant to this particular problem, take a little bit more consideration because RF pulses are in the IJ coordinate system, which does not quite as easily transform into the I hat prime and J hat prime coordinate systems, which are rotating, right? But again, we don't care about that for this problem. If you were to handle this in the rotating frame, which is what I had said in one of the sort of first email questions about this problem set, then you would need to describe the gradient system appropriately, which would just be like a gradient dotted with a position along the K hat prime direction. K hat prime is easy, right? Because it's shared with the K hat direction. So gradients in the rotating frame, laboratory frame look the same. So the point is you could have answered this question this way. That conceptually, it's okay with me if procedurally you did the right things without sort of throwing in other terms or whatever. And what this B effective would look like would be a B0 term that was offset by this fictitious field, so those two terms would go away, and you would have this gradient term left over. So you can have a gradient term, and I think this was maybe a source of confusion, but you can have a gradient can have activity as part of this B effective, the effective B field in the rotating frame. So if that was a sort of a point of departure, confusion, whatever, again, I'm not really worried about the history, I would just like you to conceptually understand that. Were you to have answered this question in the lab frame versus the rotating frame, you really still get the same answer. The principal difference being when you're talking about a range of frequencies, it's either a relatively narrow range of frequencies in the rotating frame, because it's just the frequencies that accord with the applied gradient field, so this nonlinear gradient field, or you did it in the lab frame and you had that same set of frequency offsets due to the gradients plus a B0 offset, which would give you sort of 64 megahertz, or was it 3T, I don't remember, it's 128 megahertz offset. Either solution, in my view, is fine. So again, if that isn't resolved in your head at this point, then just catch me after class, that's fine. And if you feel like that particular homework problem wasn't graded correctly for you, then just connect with me again. Good? Okay. Sorry if that wasn't clear at first. Okay, so now we're going to talk, we'll just kind of round out, we'll round out the hour and just kind of as far as we get. Handful of learning objectives here, mostly related to sort of what are these image artifacts. And the sort of fun / trick, and you're going to get some real hands-on experience with this in the lab, is when you see an imaging artifact on MR, how can do you have the tools, the machinery to think about how to undo that artifact, right? Because a lot of things happen in somewhat obscure ways in MR, or at least not entirely intuitive ways. So this one we talked about a little bit already, was Gibbs ringing, right? And I think this was in the online lecture as well, but I'll go through it. So we saw this sort of spurious ringing around sharp edges. This is really sort of more of a signals and systems problem, more so than, say, an MR-specific problem. What it results in is a maximum or minimum overshoot of about 9% of the intensity discontinuity. So we're going to see Gibbs ringing at high contrast boundaries, high signal intensities adjacent to low signal intensities. And if you think of that delta in signal intensity, the Gibbs ringing artifact on top of it will be about 10% of that signal difference. There's different ways to sort of deal with this. The result of it arises as a result of truncating the Fourier series model as a consequence of finite sampling, right? We don't sample infinitely, we sample a finite number of points, and consequently Gibbs ringing will be there in the Fourier model, if you will. There are different ways to deal with or reduce this artifact. One way is to acquire more data. That's kind of obvious. This you'll see in just a second is a resolution-dependent problem. But obviously acquiring more data is sort of easier said than done, right? It's going to cost you time at least. And the other, and you saw this some already in that very, very first slide, was that you could filter the data, which is going to reduce oscillations of the point spread function. Something we didn't specifically with the point spread function, so we'll do that next. As an example of what I'll use here, this is just, I forget what the function is in MATLAB, it might just be phantom, but you can generate these kinds of objects, and then of course it's easy to get the Fourier data for that underlying object. So we could think about sampling that object in different ways. We could sample that object with a low resolution matrix, or we could sample along the diagonal here, increasing our resolution in both dimensions until we have, say, high resolution sampling. We've gone out to farther to the corners of the space. Now, an interesting thing in MR is our phase and frequency encoding matrix size. They don't need to be the same, right? So we can pick different matrix resolutions for the x and y direction, or the phase and frequency encoding direction. And so this array of k data just shows the possibility of maybe extending the resolution in the readout direction, getting more k points in the readout direction, but I haven't changed anything in the phase encode direction. So what's that going to do to my resolution, this example here? What's the direction of high resolution? What's the direction of low resolution? What direction is going to be high resolution? X direction, readout, left, right. Yeah. So I have more k points, right? More data. There's pluses and minuses, longer echo times, longer acquisition times, but you can do it. In this direction, I have not increased the number of k points, so it's going to be lower resolution. Now, the kind of funny thing is if you're just stuffing your k data into matrix points, right? You have an array in MATLAB, and you're just stuffing coefficients into that array, and you take the 2D Fourier transform, you're going to get a kind of funny result, right? This is not true to the underlying object, but it has a one-to-one correspondence with the k data that you actually apply. And so we have to sort of deal with that. We'll talk about that in just a second. Focus for now maybe just along the diagonal, right? So same underlying object sampled with high resolution in the bottom right or low resolution in the top left. And what you'll notice is as the resolution is decreasing, that Gibbs ringing artifact becomes more and more apparent. So Gibbs ringing is really associated with low resolution imaging. That's one way to think about it. And there's different ways to increase our resolution and deal with Gibbs ringing, and so we'll talk about that. Now, so one of the problems we talked about was that if your k data is sort of rectangular and you just take a 2D Fourier transform, you're going to get a funny looking image. What you can do, and it looks like I probably took out one of the slides, you can do so-called zero padding. And so going back to, say, this data here, if what I did was a 2D Fourier transform of just the kind of the orange band of data, then I'll get a funny shaped object. If rather I add a bunch of zeros to my k-space, we call this zero padding, such that my matrix is square and full. It's full of a bunch of zeros, but it's full. With my acquired data down the middle, that's called zero padding the reconstruction. You just added a bunch of zeros, and then you regain back the proper aspect ratio, and make sure that it ensures that your delta k, which governs your field of view, is divided into a number of points that gives you square pixels. And so what you see in this case now, on this bottom left, is a little bit more apparent Gibbs ringing artifact, and it's again associated with that low spatial frequency encoding direction. So the Gibbs ringing is really kind of concentric in the, say, up-down direction, right? You don't see it as much in the left-right direction. Left-right was fully acquired high spatial frequency data. Up-down or phase encode direction was not. And you see effectively the opposite result in the top right-hand corner, right? The orientation of the Gibbs ringing has swapped. And if you go back to the K data that we were talking about acquiring, the K data was a swath of data in the up-down direction, right? A very narrow band of data in the up-down direction. So you can flip back and forth on your own to sort of see that. Again, the point is really two things. Gibbs ringing is associated with high contrast boundaries. And Gibbs ringing is most apparent in low spatial encoding directions. And what the direction of low spatial encoding or low resolution imaging is will depend on maybe your exact protocol. Now, one of the ways to deal with this, and we saw this also at the very, very beginning, was so-called windowed reconstructions, right? And so the conventional Fourier reconstruction just looks like an inverse Fourier transform. We can recover an image of the underlying object by adding up all of the spatial frequency patterns multiplied by the weights that we actually measure. So we can get our object back. The so-called windowed Fourier reconstruction just adds in this windowing function here, and you can see that the windowing weight, the weight itself, depends on n, where n is the k point in the matrix that we're talking about. It's the first k point or the last k point. N is just an index into the matrix. And so you can see it's indexing in the spatial frequency term as well. And so in one dimension, this is more specifically what that filter can look like. This is called a Hamming filter. There is, in fact, also a Hamming filter. So Hamming and Hamming, don't know why. Mathematically, they're very similar but slightly different. And you can see both in MR imaging or other signal and systems processing. The point is, this is a definition of a possible window function. And the feature of this window function looks a little bit like a Gaussian. It's driven by a cosine function. The feature of this windowing function is that it falls off to 0 on, say, the left and the right, and it's full amplitude in the middle. And so what does that mean? It means that you're going to be multiplying the middle of k space by something like 1, so just retaining that k point's value, but it's going to roll off all the way to the edges of k space where you're effectively multiplying by 0. Now this drives me nuts a little bit, right? Because why do I want to acquire data and multiply it by 0? But it does end up being a pretty good filter, and you're really only doing that to kind of the last handful of points. We can talk about that a little later. And so we talked quite a bit about point spread functions just a second ago, and this is the effect of the Hamming filter on the Fourier reconstructed point spread function. So it was, well, let's look at a top example. The top example, let's say this is our object. Our object is just some rect function. I take my rect function and I convolve it with the Fourier reconstruction point spread function. This is that direct let function that we saw 10, 15 slides ago, I remember. If you convolve those two together, then the image of my object will look something like this. It's not a perfect representation of the object. It's close. It looks kind of box-like, but it's got this funny ringing pattern in it because the point spread function itself is not a delta function, but rather this kind of sync-like direct let function. And so this isn't ideal, right? It means that at the edges, at high contrast boundaries, right, low signal, high signal, you're going to get Gibbs ringing, right? The Gibbs ringing, you can see it right here. It's this overshoot of the signal, kind of ringing of the signal. But we can do away with that. And one way to do away with that is using a so-called Hamming-weighted point spread function. And so again, bottom left is the true object. This is the physical object. The image of that object will be the object convolved with point spread function. But here we change the point spread function such that it's no longer the Fourier Recon point spread function, but the Fourier Recon point spread function multiplied by that Hamming filter that we saw in the beginning. So it's pointwise multiplication of that Hamming filter with the point spread function itself. And that smooths things out. Kind of makes sense. That Hamming filter was one at the middle, so it's going to keep the middle of your point spread function, but then it rolled off to 0. And so you can see at the edges here that ringing has been pushed down because it's effectively multiplied by 0. What's the consequence? Well, the consequence is that you can reconstruct an object that looks like this, and that Gibbs ringing artifact has obviously been attenuated a lot. So just by filtering a Hamming filter on top of your K data, you can reduce that Gibbs ringing and the point spread, the Gibbs ringing in the underlying object. So that's the benefit of this windowed reconstruction. What isn't quite clear here is that there will be a blurring of this object as well, which is perhaps a little bit more apparent here. The full width half max of this point spread function is wider, about 10% wider than just the raw point spread function for Fourier imaging. So Hamming filter, good, pushes down Gibbs ringing, bad because it decreases your spatial resolution a little bit. But on total, I think probably overall improves image quality. This is just a 2D Hamming filter, so we saw the profile before, this sort of Gaussian-looking thing going across. This is what it would look like in 2 dimensions, and then this is the example I showed at the very beginning of class. You could take your K data, you could dot multiply with a Hamming filter, 2D Fourier transform with that K data, and get this underlying image of your object. It's a little bit blurrier, not by much, but the Gibbs ringing is pushed down a lot, especially if you compare it to just taking straight 2D Fourier transform. Lots of different windowing functions, and that's, again, like I said, there's some secret sauce there that's vendor specific, so we won't get into a lot of detail there, but you could consider other windowing functions as well. All right, And so this is just going back to the zero padded data. So we took our K data, we said we better zero pad it so that we reconstruct objects with the sort of right aspect ratio, easy enough. And now if we apply a Hamming filter to our K data, that's what's in the next slide. So pick an example where there's a lot of Gibbs ringing, add a Hamming filter, and that Gibbs ringing basically goes away, of course at the expense, as I've already said, of a little bit of spatial blurring. Okay. So that's one great example of an artifact that's really related to how we sample data. Oftentimes we can associate artifacts with either being phase encoded artifacts or frequency encoding artifacts. What I said about Gibbs ringing was that it depended on high contrast boundaries and it depends on resolution, right? So lower resolution has more apparent Gibbs ringing. So do you think Gibbs ringing is more likely to be a frequency encoding artifact or a phase encoding artifact? Phase, right? Why? Yeah, so our frequency encoding happens really quickly during that readout, right? So microseconds per point. Phase encoding requires another TR. So we tend to compromise resolution in the phase encode direction just for practical reasons. And so as a consequence of it being lower in resolution, you're more likely to see phase, Gibbs ringing in the phase encode direction.
You would also double sample in the readout direction, right?
You also oversample in the readout direction, yeah. So you're sort of even less likely to see it. So Gibbs ringing, you can't exactly say it's a phase or frequency encoding direction, but some artifacts we can say that this is a phase encoding artifact, this is a frequency encoding artifact. So I'll try to highlight that during the sort of next handful of artifacts that we point to. But it's also very, it can be a useful thing when you're on the scanner and you see an artifact and you say, well, wait, what's the frequency encode direction? So okay, well, if I see that artifact going this way, that's the phase encode direction. So it gives you some insight about your imaging system pretty quickly. Some of these we've talked about already, so I won't get into it. We've talked a little bit about aliasing, we've talked quite a bit about Gibbs ringing, and we've seen this noisy spike artifact before. If a single K point is very high in magnitude for some reason, you get this banding. We'll see how many of these we get through. You've seen already, at least sort of in the mathematical sense, gradient nonlinearity. I think I maybe had an example of a gradient function for that. We probably won't get to all these, but we'll try to talk about at least the first three: noise, chemical shift, and motion. With regard to noise, the problem is relatively simply stated. So I have an image on the right that's been acquired many, many, many times, and at any pixel, I can estimate its signal intensity, and I can estimate how much that signal intensity sort of fluctuates over time. And so for some pixel that's a little bit brighter, say up here, top sort of left of the image, I have some sort of typical signal intensity. I could characterize it as the mean of this signal if I wanted to. And then I have some fluctuation, which I could describe by a standard deviation or a variance. And so inherent in this signal is this concept of sort of the signal amplitude and its variance, or the signal and its noise. And that's the basic idea behind signal to noise. If we come to some other pixel location, it may well be lower in signal intensity, but it may in fact have very similar noise, because the noise is really governed by the system. It's not so much governed by the actual pixel itself for the conventional imaging that we're describing, at least in this section. The problem with trying to measure signal to noise this way is we don't typically have dozens of the same image, right? That takes a lot of time, and so that's not usually a good way of measuring the signal to noise for a particular protocol set. And so the sort of poor man's way of doing this, to calculating the signal to noise, is just to take the mean signal intensity in a region of interest, and the region of interest should have a relatively uniform signal intensity, meaning it's a single tissue, it's white matter, it's gray matter, it's muscle, it's fat. And then we can get an estimate of the noise by looking at the standard deviation of the background and some region of interest outside of the object. So everything happening outside of the object, under ideal circumstances at least, is just a good example of the variation due to noise. There should be no signal coming from there, so any fluctuations are really noise driven. There's a lot of subtlety and specifics to how we really should measure signal to noise, but this is sort of as I've said here, a method of measuring the signal noise is widespread, but it's imperfect in some sense. So if you really go down the avenue of MR research, you probably shouldn't do this, but this is still pretty widely done. And the assumption here, and we'll get into this in just a second, but the assumption, for example, in this noise region of interest here, is that the signal fluctuations we'll get into this concept a little bit, but within a region of interest like this, the variance over space is expected to be the same as the variance over time. And this is the concept of noise being what we call ergodic, that variations of the signal over space or over time are the same. They're driven by the same concept of sort of thermal fluctuations driving small perturbations in the signal itself. And so we can, because we assume the noise is ergodic, an average over space is equal to an average over time. That's an assumption that's not always a good one, and that's why I'll say it again, that this is a really widespread way of estimating signal to noise, but it's actually not quite true, because in point of fact, you can have variations in noise over space that are different than those over time. And so we have to be maybe a little bit careful. This, almost a repeat of some of the previous slide, just describing or giving a definition for the signal to noise. This should really probably say like the mean signal amplitude divided by the standard deviation of the noise. And I'll give you some insight as to why or what factors affect the signal to noise in imaging. And we've talked going back, I think maybe even the first homework assignment, about this concept of contrast, which requires thinking about signal differences between two different regions of interest, white matter and gray matter, and then again just dividing by the standard deviation of the noise. We oftentimes care about contrast in MR, and so consequently we care about the contrast to noise difference. All right, and so this movie, it's not playing really smoothly for some reason. What it's supposed to be showing is an image on the left that's corrupted with greater and lesser degrees of noise. And the point is that as the noise gets to dominate the underlying signal, the K data itself just looks like noise. So the Fourier transform of noise, of a pure noise object or a pure noise image, is also noise-like. There's this linear transformation, so the linear transformation of noise through the Fourier transform is in fact just noise. And I want to give you a little bit of insight about the relationship between sort of the variance of signals in image space and the variance of signals in the Fourier space, and how that affects our estimates of noise in MR images. And so the next thing, hopefully this part works, we'll switch over to the board and I'll just work through some notes for a moment. All right, so in the Fourier domain that is in K-space, we can say that our signal, which is sampled over different K points, is, say, the perfect signal S of K, potentially corrupted by some noise, which we call the C, D being the data noise, which could also vary over K. So this is just meant to be, this is sort of data noise. Most of the noise, the way these systems are designed anymore, the hardware architecture is actually extremely good, and the noise has been pushed down substantially, meaning there's not a lot of noise in the receiver system itself. The noise actually is dominated by what we call body noise, and that means that as a human individual that's basically a big bag of salt water and conducting fluids, there's signal fluctuations in our tissues that contribute more noise, called body noise. Body noise is actually greater than the hardware and the receiver system noise. Is there a question in the back? Did you guys see that? So this is just saying the true signal on the left-hand side is the superposition of the measure, the ideal signals, the SOKs, plus some underlying noise. And we can consider the same thing in image space. And so in image space, we could say, well, fine, we have some corrupted image, which in this case varies one-dimensionally over space, x. And that's just the superposition of the real image, if you will, or the perfect image, if you will, plus some corruption that's coming from image noise. So this here we call image. So the Fourier reconstruction problem. Let's consider the case where all we had was noise, right? And so what if the underlying image here was really just the zero image? Then we can think about the Fourier relationship between the image noise and the data noise. And so from the Fourier reconstruction problem that we were talking about earlier in the lecture, we can see the connection between the underlying image noise and the k-space noise, if you will. So it's just 1 over n. This is n over 2 minus 2. We're adding up all of the data noise, that is the noise at every k point, if you will, and it's just multiplied by the spatial frequency wave. So this is just the Fourier relationship between noise in the image domain and noise in the data domain.
It's a positive I.
What's that?
It's a positive I.
It's a positive I.
Yeah. I know we use.
Oh yeah, sorry, for the Fourier coefficients. Yeah, I think so. And then in this case here, we would have this would be for let's see, minus n over 2 less than or equal to n less than or equal to. This is just saying that the image noise that you get arises as a consequence of the linear Fourier transformation of the underlying data noise, the noise for each of these k points that we measure at k points, but we do it imperfectly, right? And in the movie that didn't work so well in the previous slide, what you would have seen was that the Fourier transform of image noise looks a lot like noise in the Fourier domain. It's hard to distinguish between the two. So what are the properties of our data noise? So in our imaging system, we make a few assumptions about the actual data noise, and so we can describe the characteristics of the noise with sort of several different terms. So one is we refer to as additive. In addition to being additive, it's ergodic. This is what I was talking about just a second ago. And ergodic means that the average over space is equal to the average over time. We think of the noise as stationary, meaning it's specific to a location being sampled. It's not somehow sort of drifting, moving, somehow changing across the object itself. It's also uncorrelated, so that means that there's no space, I should say it's uncorrelated in space and time. That just means that the noise at a particular k point and or the noise at a particular image point are independent, right? They're not correlated somehow to one another. These are assumptions. These aren't perfectly true, but in the simplest case they are. We also assume that the noise is what we call white noise. And white noise means it's got an equal intensity for all frequencies. There's a laundry list of things here, right? The other second last one of this is that it has zero mean. And so any fluctuation to the signal that we're measuring doesn't need sort of bias, right? It comes in as plus minus some value with a non-zero or with a zero mean. And then the last thing is that the noise itself is Gaussian distributed. And this is in fact a good assumption, and we can say that it's Gaussian with a standard deviation equal to, we'll just assign as sigma d. So in the data domain, the standard deviation is sigma d. We can think about this all because the Fourier transform is a linear operator. And all of these properties that hold true in the k-space domain, right? This left-hand side is all k-space stuff. That's going to also be true of things happening in the image domain. It's a linear transformation, so a property that's true in one space is going to be true in another space. And so what that means is that for the noise in the imaging domain, we could describe it as having a variance in the image domain. And it's, I think it'll come up here in a sec. No, okay, so this is just a laundry list of sort of properties of noise associated with MR imaging. Not every one of those assumptions is always perfectly true, but it's the assumptions that we'll make from them. So now I'm going to move this up just a little bit. And what's not obvious, but in fact really important in MR imaging is the relationship between the two variances. So we've got the variance in the data domain and the variance in the imaging domain. And the relationship between those two is that the standard deviation square, the variance, is equal to 1 over n, where n is the number of total data points or total sample points times the variance in the data domain. And so this is actually really interesting, right? Because what this is actually telling us is that this process of Fourier encoding is equivalent to the endpoint averaging. And that's not an entirely obvious concept. This is work that came from, sort of early spectroscopy work. But this is really interesting, right? Because what it says is that in the imaging domain, our variance is going to go down, 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 down with the more sample points that we acquire. And the kind of the sort of logic behind that is that while in the data domain in k-space, you're sampling a single point, right? A single k point. That single k point that you're measuring is regarding a signal from the entire object, right? The coils are really, in principle, sensitive to the entire object. And so if you're sampling lots of points, then you can push down the noise in the data domain to give you a lower variance in the imaging domain. Maybe not an entirely sort of intuitive concept, but an important one, because it'll come in just a second to our understanding of the signal-to-noise dependencies for MR imaging. And so that's kind of the last part of this. So basically, it is sort of showable or derivable. We use this as the starting point for understanding what parameters we can change in an MR experiment to improve the signal-to-noise, or if you wanted to make the signal-to-noise worse. And so that equation there, we can just simplify a little bit just by writing that sigma I is equal to 1 over the square root of n, just taking the square root of both sides of sigma data domain. And so that tells us about the standard deviation of the noise, standard deviation of the signal rather, relationship of the imaging domain and the data domain. So this was the bottom, this was the denominator of our signal to noise expression. Right? So this is the denominator of the SNR expression. It tells us about the noise. So then the question was, well, what's the signal? The signal in the imaging domain, the amount of signal that you get, it depends on a lot of things, right? It depends basically on the state of the transverse magnetization at any point in time, and also on the size of the pixel that you're trying to measure. Right? You're going to get more signal from bigger voxels, you're going to get less signal from smaller voxels. And so the signal that you get from a particular pixel is dependent on 1 over n delta k. We've seen this expression a couple times today. This was what we call the Fourier pixel size. And if we want to write that in terms of the field of view, then we can just write this as the field of view divided by n. And that should make sense. It basically just says that the signal you're going to get from a pixel is going to depend on the field of view divided by the number of points, because that will govern how big or small your actual pixel is. And so with these two expressions, an expression for the noise and an expression for the signal, we can now define the signal to noise. And we can say that the signal to noise, I should have been, sorry, a little bit more careful. This would really be sort of proportional to, right? There's other things that play into that, like the RF pulses used to generate the state of the transverse magnetization in the first place. But we know it's linearly proportional to voxel size. And so now our signal to noise is just the ratio of these two things, of the signal for a particular pixel location divided by the variance. And so that just looks like the square root of n divided by n delta k sigma d. And if we want to write that in terms of the field of view, then we could write it as the field of view divided by square root of n times sigma. And so this is kind of interesting, right? So the signal to noise that you're going to get for a particular experiment that you're doing, it's proportional to the field of view. So bigger fields of view in combination with fewer sampling points are going to give you more available signal. N is kind of complicated though, right? N is your matrix size. So N dictates your resolution, but it also dictates your scan time. And so the number of encoding points has this relationship now. It's a little more complicated. It's 1 over the square root of the number of sampling points. So part of you says, oh, if I increase n, my resolution is getting better, my pixels are getting smaller, so increasing n, well, that must drive my signal to noise down, because now I have tiny, tiny pixels. But then part of you says, well, hold on, but if I'm imaging more matrix points, I'm getting more data, I'm imaging for a longer amount of time, and that should give me back signal to noise. And the trade-off between those two is such that you finally have this 1 over square root of n dependence on the number of sampling points. And that's it's a good thing and a bad thing, right? It's hard to improve your signal to noise by improving the number of sampling points, by increasing the number of sampling points. You get there kind of slowly. It makes your pixel size smaller, but your acquisition time is longer. So again, everything in MR is basically trade-offs. Yeah. So that's the last point I wanted to make here, at least in terms of how things like your field of view, a number of encoding points, and then you don't really know what the variance is. It's something you would have to measure for a particular experiment to give you the actual signal to noise. But that's one of the simple expressions for signal to noise. So what we'll do is we'll go back to sort of seeing how this really plays into sort of more practical acquisition parameters, and that'll be the last thing that we touch on for today. So we know this already, right? You expect at least that the signal to noise is going to depend on a lot of things, right? It's going to depend on whether you choose a gradient echo or a spin echo. It's going to depend on your TR, your TE. Did you use an inversion pulse? It's going to depend on your flip angle, right? All of these things that dictate how much transverse magnetization you have to begin with, or have at all. It's also going to depend on your field of view. We saw that in the last sort of derivation. The fewer points we have, the larger our field of view. We have coarse resolution, but coarse resolution is big voxels that give us lots of signal. So we can change our signal to noise by adjusting our field of view. Something else that is not unexpected is that there should be some dependent on the slice thickness, right? If I have really, really thin slices, I don't expect to get much signal from them. If I have really, really thick slices, I expect to get more signal, but there's, again, some trade-off between slices that are too thin and slices that are too thick. And then, of course, it depends on the matrix size, and we can independently control that in the readout direction and the phase encoding direction. And then the last thing, we've talked about this a couple of times, but another thing that this should all depend on is the bandwidth. And this is the frequency encoding bandwidth, not the excitation bandwidth for the RF pulses, but the receiving bandwidth. And we can choose, again, the bandwidth that we use for imaging. One of the easiest ways to think about bandwidth is it's related to the rate at which we're acquiring data. And are we moving across K-space really quickly with a high bandwidth readout, or are we moving across K-space really slowly with a low bandwidth readout? Low bandwidth, moving slowly through K-space is going to be better signal to noise. When you zip across K-space quickly, you're going to have more noise that is relative to the signal that you acquired. And so what this, in the simplest sense, comes down to is that our signal to noise is proportional to, and we always write it as proportional because there's a bunch of imaging stuff in there, right? There's a whole sort of MXY term in here that we're not showing. We just leave it as an approximation. And it depends on what looks like the voxel size and the square root of the scan time. The square root of the scan time here, we'll talk about in just a second, but you saw it in that, saw something similar in the signal to noise expression that we had just on the derivation a second ago. So probably obvious at this point, if you have large voxels, that's going to give you more signal. The downside to having large voxels is that means lower resolution. So you have to make that trade-off or make that call between low resolution and high signal to noise, or high resolution and low signal to noise. The other component here is time, right? So longer scan times will increase your signal to noise, but you have to image by, say, 4 times longer to double your signal to noise. So increasing signal to noise by imaging more comes at kind of a steep penalty, whereas you can make small changes in your voxel size here, you get relatively good boosts in your signal to noise. So bottom line, high resolution imaging and fast imaging combined are going to compromise your signal to noise, but of course that's what everyone wants. They want high resolution images. So again, figuring out those trade-offs. The voxel volume itself, it's just geometric, right? So it's a consequence of the slice thickness and something like your X and Y resolution, where we think of resolution as just being the dimensionality of the pixel, or the field of view divided by the number of encoding points. So you can think geometrically very easy about what the voxel volume is. The square root of t, this time component here, it depends on a few different things. It depends, for example, on the number of encoding points in the readout direction, the number of encoding points in the phase encode direction, and in fact, we could do 3-dimensional imaging, so there could be a second phase encode dimension, or you may choose to do averaging, where you repeat the acquisition more than once. And that's the amount of time spent acquiring data depends on those things, and it's inversely proportional to bandwidth. High bandwidth means you move across K-space quickly, so this time is going down. So again, trade-offs there. When it comes to really practical things, and you'll see this in the lab next Wednesday, on the console there's what they call R-SNR, relative SNR. When you open up a protocol, by default, the SNR of that sequence is 1. and using this equation, it will increase or decrease your relative signal to noise depending on how you change protocol parameters. And so if you, for example, increase your field of view, which decreases your resolution, you can see your relative SNR will go up on the scanner. It's a useful thing because it tells you, and we'll talk about this in a second, but what's otherwise a somewhat complicated expression here for the dependencies of the signal to noise on sequence parameters. On the console, it can quickly calculate that and tell you if the change you've made is going to increase or decrease your signal to noise. Now it's relative because they don't know what the real signal to noise of your acquisition is going to be. It just takes that default protocol as 1. So in lab, your first protocol will have an RSNR of 1, and then it'll be your job to sort of keep track of what's happening to the signal to noise as you make protocol adjustments. You can change the field of view, you can change the number of encoding points, you can change the slice thickness. All of this stuff here is all about voxel size, right? On the right-hand side, the square root expression, this is all stuff that governs time, how quickly you get your image. How many points did you acquire? If these things go up, it takes obviously more time. If your bandwidth goes up, that actually means less time because it's this 1 over bandwidth relationship. You can rearrange the different number of encoding points that show up in there. I guess it didn't do it. I thought this expression was going to rework itself to have the ends all in one place, but at the same time. And so I know we're bumping up against the time here, but let's just think quickly about maybe this first example. If I have the slice thickness, right, my voxel volume goes down by a factor of 2, right? If I want to get back my signal to noise through averaging, for example, if this has gone down by a factor of 2, then I have to have 4 times as many averages, because there's 2, to regain the signal to noise. So decreasing your slice thickness, fine, it has an impact on your signal to noise, but it's very costly in terms of time to regain that through averaging. And I won't go through these other examples, but I think you should do that in your own time, especially in advance of the lab operates there. But I think there's 1 or 2 more things that I could go through, but we'll save the rest of this for the next lecture where we'll talk. We'll round out the artifact stuff, and we'll talk about some fast imaging approaches as well. But think through example 2 and example 3. If they don't make sense, maybe we'll do that at the beginning of the next class. But good working examples of some of this expression. All right, very good. Thanks, guys.